Hello everyone, welcome. What we will do today is we will apply what we have been doing this week is we are applying force method for analysis of statically indeterminate beams and frames. Today we will see how to use method of consistent deformation for indeterminate beams. Okay. Now, let us take the first example. The first example is a two span, it is a continuous beam, two span continuous beam. Which is subjected to an uniformly distributed load. Okay. Now, if you remember the steps of method of consistent deformation, those steps remain same. In the last week, we applied method of consistent deformation for indeterminate trusses. The steps that we discussed, exactly the same steps, but since here internal forces are different, there will be slight modification in the equation that we use in different steps. Okay. Now, the first step was, if you recall, the first step was determine the static indeterminacy. Now, look at this structure. This is an indeterminate structure, and if we remove support B, then it becomes a simply supported beam subjected to UDL, and because of the presence of support B, it is now indeterminate. So, in this case static indeterminacy is 1, and what is the kind of indeterminacy? It is external indeterminacy, because the indeterminacy is due to the support reaction. Okay. So, once we understand, once we calculate the static indeterminacy, the next step is to identify the redundant force or redundant moments. Now, let us take By as redundant force. Let us take By as redundant force. Okay. This By, the vertical reaction at Y as redundant force. Okay. Suppose this is equal to x1. Okay. The reason I am writing it as x1, because if you remember in the truss problem, when we had multiple the static indeterminacy is more than 1, then this is how we identified each redundant forces. This we denoted each redundant forces x1, x2, x3 and so on. Okay. In this case, we have just one redundant force. Let us write it as x1. Okay. Now, let us see how we can proceed with the calculation. So, the structure, the problem what we have in hand is this. This is which is subjected to uniformly distributed load 10 kilonewton per meter. Okay. Now, this is A, B, C, this is 10 meter and this is 5 meter. Okay. Now, we have already done step 2, we identified the redundant force, Ns is equal to 1, Ns is equal to 1 and x1 is By, that is the redundant force. We have just one redundant force. Now, the next step, the step 3 is we need to now first, before we proceed for step 3, now we need to remove this redundant force and get the primary structures. So, this is the primary structure. This is the primary structure which is subjected to external load A, B, and this become 15 meter. Okay. And then another primary structure which is now subjected to an unit load. So, x1 is equal to 1. Okay. Now, this is 10 meter and this is 5 meter. This is A, then B, then C. Okay. Now, step 3 is find out the deflection, associated deflection in the primary structure due to the external load, and step 4 is find out the associated deflection in the primary structure in the subjected to the redundant force. Okay. Now, this is a simply supported beam which is subjected to UDL. So, we know that if we take any section at a distance x, then this becomes mx becomes in this case it becomes 75 x minus 5 x square, that you can easily check. W L by 2 x minus W x square by 2. Okay, this is mx. W is equal to 10 and L is equal to 15 meter. Okay. So, this is equal to capital M. Okay, let us write this as capital M. Similarly, what is the small m here? What is the bending moment diagram for this? If we recall, this is a simply supported beam subjected to concentrated load at some distance. Then the bending moment diagram of this will be like this. Bending moment diagram will be like this. This is A, this is B, this is C, this is W, L, W, A, B by L. Bending moment bending moment is shown here the downward, because for this case this load is acting upward, and therefore, the deflected shape of the beam will be like this. So, the bending moment that will be generated, it is hogging bending moment, because this load will cause a hogging in this beam. So, hogging bending moment is negative as per our sign convention, that is why it is drawn like this. Okay. Now, what is small m? Small m means the bending moment due to the unit load in the direction of redundant force. So, small m is equal to, in this case the vertical reactions will be, if you see the vertical reaction, this vertical reaction will be, this reaction will be 5 by 15 means 1/3, and this reaction will be 2/3, that you can easily verify. Okay. So, m will be, if we take a section between, this is x, this is x, then m will be, this value is x, then m will be minus 1/3 x, when x is between 0 to 10. Okay. And moreover, x is measured from x, from A. X is measured from A. Now, if we take this, so this is the bending moment between this is the equation for this line, bending moment between A and B. So, bending moment between B and C will be m, which is m. In order to get that bending moment, take a section here, which is distance x, like this. Okay. We could have taken distance x from this support as well, but we will see that if we take distance x from C, this expression becomes simple, and this expression will be minus 2/3 of x. Okay. And in this case, x is between 0 to 5, but this x is measured from C. Okay. This please be careful. Okay. So, this is essentially equation of this line, but this x is measured from C. Okay. Now, great. So, once we have this, next step is we need to solve it, right. We need to find out the displacement at point B, vertical displacement at point B due to this externally applied load, and suppose that displacement is equal to dl1. If you recall, in the last week, this is how we denoted the displacement or the associated displacement in the primary structure subjected to externally applied loading. Okay. So, dl1 is essentially the displacement due to the displacement in the primary structure due to the externally applied load, but that displacement in the direction of x1, and this x1 is the value of x1. That direction is the value of okay, fine. Now, this is equal to, if you recall unit load method, that is m into small m divided by EI. EI is constant in this case into dx, right. Now, this expression can be divided into two parts. This is over the entire length 0 to 15, and this expression, this integration can be divided in two parts. One is between A to B and then between B to C, because the expression for bending moment are different for different parts. So, this becomes 0 to 10, and then m is this value 75 x minus 5 x square, and then between 0 to 10 this is the value of small m. So, this is x by 3 minus x by 3 dx. Okay. So, this value it is from 0 to 10 plus then 75 x minus 5 x square. This is between B and C, and then again this is minus 2/3 of x dx, and this is 0 to 5. Okay. Please note that this expression remains same whether you calculate, whether you take x from this side or x from this side, because it is a symmetric symmetric loading. So, this is dl1, and if you do this integration, the value what you get is dl1 is equal to, I am not doing this integration here, minus 5729.2 by E I. Okay. So, this is the displacement in the primary structure due to the external loading, and this displacement is in the direction of redundant force. So, this is dl1. Okay. Now, if this is dl1, next step is to find out the deflection in this structure due to this unit load, and that deflection is essentially the flexibility coefficient. So, next we need to find out what is F11, what is F11 for this structure, for this F11 for this. Okay. Now, what is value of F11? F11 will be 0 to 15, because this is the total length. Then M1 into, in this case there is no M1 because it is just only one redundant force. So, it is M into M by EI dx. Okay. And the expression for M, we know that this becomes 0 to 10, x is x minus x by 3 whole square dx 1 by EI, and is equal to plus 0 to 5, it is again minus 2 by dx 1 by EI, 1 by EI. Okay. And this become F11 if you do this integration, and this become 55.556 divided by EI. Okay. This is. So, then this was step 4. Then if you recall, step 5 was applying the compatibility condition. What is the compatibility condition we have? Compatibility condition is at this point displacement is equal to 0 because it is supported. So, compatibility condition is that delta dl1, which is the displacement in the primary structure due to the externally applied load, plus by plus x1, which is the redundant force, into F11, which is the flexibility associated with this redundant force, is equal to 0. So, this gives you the displacement in the primary structure due to the external applied load, and this gives you the displacement in the primary structure due to the redundant force. Okay? And F11 is the associated flexibility coefficient. So, this is equal to 0. Then if we substitute the value of dl1, dl1 is equal to minus 5729.2 by EI plus it is 155.556 by EI into x 1 is equal to 0, and finally we will get x 1 is equal to 103.12 kilonewton. Okay. Now, once we get x 1, the value of x 1 in this problem, value of x 1 means then b y is equal to this is equal to b y. So, we know what is the value of b y. Now, with the knowledge of value of b y, now the structure becomes determinate. We can find out, we can draw the free body diagram of the entire structure, apply the equilibrium condition, and then find out the other support reactions and member forces. Okay. Now, this is the first problem. Okay. Now, let us take the step 6 is that apply the once we know the redundant force, apply the equilibrium, draw the free body diagram and determine the other unknown forces. That is the step 6. Step 6 we are not doing here because we have done it several times in several problems. Okay. Let us take another example. This example is similar to the previous example, similar in a sense the length and the loading condition, but only difference is the pin support which was at A, that is now replaced by one fixed support here. If you see, that is now replaced by one fixed support. Okay. Now, then what happens? What is the indeterminacy we have? What is the indeterminacy we have in this problem? We once we replace hinge support by a fixed support, means we are adding one additional constraint, that is rotational constraint, right. So, we are for that the indeterminacy of the structure is increased by 1. So, in this case, now what is the indeterminacy? Indeterminacy of this problem will be Ns is equal to 2. Because if we remove B and C, support B and C, then it becomes a cantilever beam which is stable and determinate, and because of this additional constraint the structure is indeterminate and degree of indeterminacy is 2. Now, the next step is the choice of redundant forces. Now, there you have when you have multiple redundant forces, more than one redundant forces, then your choice has also become more. Okay, but you have to choose those primary structure which are determinate as well as stable. Okay. Now, in this case, you can have some choices like we can take by as redundant, by and cy as redundant. This is one choice. Another choice is we can take ma and by as redundant. Okay. These in both the cases the structures are determinate and stable. What we do is we go with this choice. Okay. We will take the rotation at the moment at A and the support reaction at, so this moment and the support reactions at, so this is by and this is ma, we will take these two as redundant. Okay. Now, then this is, say, this is x 1, this is x 1 and this is x 2. Okay. Now, okay. So, let us find out, let us see how we can proceed with this method of consistent deformation. Now, the first is the step 1 and step 2 are done, then the step 3 we need to solve the primary structures for different loading condition. So, since now we need to solve 3 determinate structure, one is primary structure subjected to the external load and then 2 primary structures which are subjected to 2 redundant forces. Okay. Now, this is the first structure, primary structure which is subjected to the external load. Okay. Then second primary structure which is subjected to unit load, and then third primary structure third primary structure which is subjected to unit moment. Okay. This is 10 meter. This is A, C, A, B, C, A, C. Okay. Now, let us just divide this into 3 parts. Okay. Now, this is already we have done, right. Now, this is x 1, in this case it is x 1 and in this case it is x 2. The redundant forces is x 1 and x 2. Now, what is the expression for m? Expression for m just now we have seen that 75 x minus 5 x square. Okay. Now, let us find out what is m 1 here. What is m 1? If you remember, just now we wrote what is m 1, and the m 1 is minus x by 3, and when between a and b, when x is between 0 to 10, and this is from a, measured from a, and then m 1 is equal to minus 2x by 3 minus 2x by 3 between 0 to 5, it is measured from B. That we have done it just now. Now, for this case what will be the bending moment diagram? The bending moment diagram for this problem will be something like this. Okay. This value is 1. This will be the BMD, bending moment diagram for this. And what is the expression for M2? Expression for M2 will be it is 1 minus x by 15. If x is measured from A, otherwise its value will be x by 15 if it is measured from B, from C. Okay. This is important, from C. Okay. So, if you take a section, if you take any section, if you take any section, and if you take x is this value, then this is the bending moment expression for bending moment, but if we take x is this value, then this is the expression for bending moment, which is obvious from this figure. Okay. Now, next step is what we need to find out. We need to find out the displacement in the associated displacement in the primary structures, and then corresponding flexibility coefficients for this. So, we need to first find out what is DL1. What is DL1? DL1 is the displacement in the primary structure due to the externally applied load, and that displacement is in the direction of first redundant force. Okay. So, DL1 is essentially displacement at B, and then we need to find out what DL2. DL2 will be the displacement in the primary structure due to the external load, and that displacement is in the direction of x2. So, DL2 will be essentially the rotation at A. So, and we know from unit load method DL1 will be, this is 0 to 15, this is m into m1 by EI. Now, m expression of m we know, expression of small m1 is this, and then if we do that, it is exactly same. We have already determined it, that DL1 will be in the previous example that 5, 7 to 9.2 by EI. This is DL1. This is DL1. Okay. Now, similarly, we need to find out what is DL2. DL2 will be it is just straightforward implementation of unit load method, M2 by EI. Okay. So, DL2 will be essentially the rotation at rotation at A due to external applied load. And what is the value? You can substitute m from this and small and m2 from this, and if we do that, this expression becomes 1406.3 by EI dl2. Please do this integration and check these values. So, we have obtained dl1 and dl2, the displacement in the primary structure due to externally applied load. Now, what we need to find out? We need to find out now the flexibility coefficients. F11 will be integration m1 square by EI dx 0 to 15, and m1 is this, and if we do that, that is equal to 55.556 by EI F11. This is F11. Okay. Similarly, we need to find out F12. F12 is the flexibility coefficient associated with displacement in the direction of x1 due to unit load in the direction of x2, or we can say it is displacement in the direction of x2 due to unit load in the direction of x1. Both are same because the matrix is symmetric matrix. Okay. So, these become m1 m2 divided by EI dx 0 to 15. Okay. And if you do that, then F12 comes, F12 is minus 11.111 by EI. F12 is this. Okay. So, we have already determined F11, F12, F12 and F21 will be same. Next, we need to determine what is F22. F22 will be m2 square EI dx. Okay. And if m2 is this value, and that becomes F22 become 5 by EI. 5 by EI. Okay, you can check it. Okay. So, we have almost all the informations available. We know the displacement in the primary structures, also we know the flexibility coefficient. Next step is apply the compatibility condition. And what is the compatibility condition? Compatibility condition is DL1, DL2, similar compatibility condition we have used for truss problem as well. This is F11, F12, F21, F22, and then x1, x2, this is equal to 0. What it means? It says that displacement, if we see here, it says that displacement at point B is equal to 0, and this rotation at point A is equal to 0. Okay. Now if we substitute all these values, DL1 is equal to minus 5729.2 and then 1406.3 plus F11 is 55.556, F12 minus 11.111, F21 will be same as F12, and then F22 is 5 is equal to 0. Now, if we solve it, then we get x1 is equal to 84.37 and x2 is equal to 93.77 minus. Okay. So, what was our x1? x1 is equal to support reaction By, support reaction at By and x2 were M A. So, for this problem we have already now these with the information of By and Ma, now the structure is determinate. We can apply the, you can draw the free body diagram and apply the equilibrium condition to get the other support reactions and internal forces. Now, we can draw the if you have to draw the bending moment diagram for this problem. Let us draw the bending moment diagram. This was A, this was B, this is C. Okay. Now, one approach, as I said, you see this bending moment is negative, this bending moment is negative. Okay. Now, or one way is you draw the and if we apply the equilibrium conditions, then we get that MB is equal to I am not doing it, you can check it please, 62.5, this is negative kilonewton meter. Okay. 62.5 kilonewton meter. Okay. Now, then MA is 90, MA is, this value is 93.77, and then this value is 62.5, and then due to the redundant forces the bending moment is, and then constant at, because at C it is 0. Now, what is the bending moment due to the external applied load? Bending moment due to external applied load is this. Okay. Now, if you superimpose that on this, then your final bending moment diagram become like this. So, this is bending moment diagram, okay, not the green one. So, your bending moment diagram become this part. So, this is bending moment diagram. The advantage of drawing the bending moment diagram like this, you do not really have to specify the sign. Now, whatever bending moment below this, it is hogging bending moment, and above this is sagging bending moment. Now, just try to guess what would be the deflected shape of this structure. The deflected shape of the structure, there is a support here, there is a support here, and there is a support here. So, naturally at this point slope will be 0. So, deflected shape you may get, please verify this, please deflected shape something like this you may get. Okay, or if it is not something like this, you may get. Another the reason I am drawing the bending moment deflected shape here is, you see, by just looking at the bending moment diagram and the support condition, we should be able to have some understanding about the deflected shape of the structure, because you see, naturally in this case between this part it is hogging moment. So, whatever way this beam deflects, the deflected position will be hogging position, and between this part and this part it is sagging moment. So, between this part and this part the beam will sag, and again between this part and this part the beam will there will be hogging, and again between this part and this part the beam may sag. So, so based on that you need to identify this deflected shape. Okay. This deflected shape is not drawn in scale. You may have this deflected shape, or these values will be very small. If these values is very small compared to these, that deflected shape may look like differently. But the point is, it may deflect like this, or you may have this very small value something like this. Okay. So, whenever you solve any problem, whether determinate structure or indeterminate structure, whenever you draw bending moment shear force diagram, parallelly you try to draw the deflected shape, try to understand, try to by intuition you try to find out, try to guess the what could be the deflected shape, and once you draw the deflected shape, then later you find out the deflection and compare whether your intuition was right or not. These exercise will help to develop the sense through which, without actually solving a structure, you can have some understanding of the behavior of the structure. Okay. Now, what we do is we stop here today, and then next class we will see how the method of consistent deformation can be applied to frames, indeterminate frames. Okay. See you in the next class. Thank you.